Hello, everyone. So let's continue our second half of this session. So I'm Xiaowei Jia from the University of Pittsburgh. And so our first speaker for the second half is Dr. Yan Liu from the Computer Science Department at the University of Southern California. So let's welcome Dr. Yan Liu.
Yeah, thank you very much. I'll just start sharing the screen. All right, hi. Hello, everyone. Good afternoon. Thank you very much to the organizers for inviting me. And also, I'm going through some of the talks in this wonderful workshop. I think I've learned a lot myself. So in this particular talk, I'm going to zoom in one specific topic in this big domain in knowledge-guided machine learning. So basically now we are going to talk a little bit of how we can use the domain knowledge, for example, the physics information, to help the data-driven approaches. For example, these graph neural networks. And specifically, I'm going to talk one special type of neural network, that is the differential graph neural network, and to show how we will be able to incorporate domain knowledge naturally and effectively. So in this particular workshop, I've seen a lot of really exciting applications. For example, there has been lots of talk around climate and weather, and there also has been some discussions about potentially other physical world applications such as transportation, power system, and etc. All these applications involving physical world were basically confronted with the spatial temporal data. One of the key challenges for machine learning researchers like me is how we will be able to build effective machine learning model so that we can actually consider the spatial and temporal dependencies among these physical world data so that we can achieve good prediction performance or learning performance in different tasks. For example, we can do forecasting, classification, clustering, and maybe reinforcement learning in the longer term. So in this particular talk, I'm going to focus on the forecasting task, but the methodology is obviously generally applicable to many other machine learning tasks and in this physical world application. So when we talk about these data-driven approaches and we want to build the machine learning model from the data, one of the things that we always want to ask the question is how we will be able to actually fully utilize the data, and also can the data tell everything about training the model? So when we look at all the existing successes for machine learning for these data-driven approaches, that we have seen that they were able to get significant advances. But on the other side, they also faces a series of challenges or issues in the practical application. For example, in here, one thing is that it will be very easy for them to learn the predictive models for predicting labels, but a lot of the time that they are not very good at learning explicit information on models. For example, in here, we show a specific example where we're looking at an example in the physical dynamics. So in here that we're interested in the state, that is the position and the velocity. And the input will be the current state and obviously also the historical states. And then the output is the next state. The model will be able to do a reasonable job to predict the next state. However, it will be very hard to learn the implicit rules, such as some of the energy and momentum conservations. And that's exactly a lot of all this really wonderful research work have been conducted across different domains in physics, in math, in related areas to actually learn these energy and momentum conservations to learn the fundamental rules. Well, for data-driven approaches, we're more interested basically on the predicting labels and the outputs that we're interested. And the second challenge we're facing is that when we try to learn the data, it's more on a specific distribution. And when we are confronted with a series of other challenges, for example, we try to add some adversarial text, then this could raise significant challenge. Some of the examples we have seen a lot is in computer vision application, where you can build a perfect model to predict cats or dogs. But on the other side, if we add some adversarial noises in there, then the model can easily fail. That means that we need to also look for a lot of these robust solutions so that we can utilize some of the domain knowledge to help improve the data-driven approaches. The third is also, it would be very hard to get high quality label data set. So when we talk about high quality, this ranges significantly from application to application. For the application we have been working on around physical world application, a lot of the data coming from the sensors or from the satellite, and that means that some of the sensors could be broken, some of the sensors have been distributed across different locations, and that means we're getting a large amount of scattered irregular observations. And if we want to build a really good model from these relatively low quality data using the data-driven approaches, we also will face significant challenge in terms of the noise, missing values, irregularity, and things like that. So that means that all these challenges demand a strong and generalizable inductive bias so that we can get a more robust and also efficient machine learning model. And we have talked so much about physics aware, and therefore that I don't think I need to give too strong motivations for why we want to use the physics information in there. Some of the challenges I already mentioned, for example, the data we collected, for example, the climate, air, sea surface data, these are all very much scattered irregular time series or spatial temporal data. And also from the spatial temporal observation perspective, there's also a lot of these explicit rules, constraints from physics we can utilize and hopefully can benefit. Last but not the least, hopefully that these rules will be actually helpful to the data or domain agnostic so that they can generalize these inductive biases so that we can achieve a robust and generalizable model. I think the major challenges for us to utilize the physics knowledge in our specific neural network or other machine learning model is how we can effectively incorporate them inside the model. And obviously different type of research have been working on this. We all know that for the physics knowledge, they are more or less defined on a continuous domain. On the other side, most of the data that we have observed is basically on the sparse, irregular observed data points. And how we will be able to actually talk between these continuous domain knowledge versus irregular sparse observations, that is really the challenge that we have to handle. If we are able to do this effectively, hopefully we will be able to achieve very good prediction performance. The key challenges we're addressing here, as I motivate just now, is how we can actually build the bridges between the continuous domain to the sparse and irregular observations. So in this particular talk, I want to motivate and also trying to show you some examples how we can actually utilize a very nice signal, that is the graph signal, to effectively represent the sparse irregular observations using the graph signal. And then we can also utilize some of the properties on these graphs so that we can represent the domain knowledge over the graph, so that effectively we build a channel between the continuous model domain and also the sparse irregular observations. And that is basically what I want to achieve in this particular talk. That is answer the question how we will be able to represent both the continuous domain graph and also the relational information between the observations that we collected. And then we will be able to get really good and effective model. Our journey actually started from a very different starting point, and we gradually get ourselves to where we are right now. When we talk about the input, basically we're going to get the sensor-based observations of the physical system. This can be weather data, air quality, sea surface dynamics, or extreme weather events. And then in terms of the physics knowledge, it also covers a wide range. This can be the partial differential equations that everyone is talking so much about. And this can also be some physical properties, geometrical properties, some physical principles, and etc. And now we want to incorporate them together, building a hybrid model so that this can be a physics-aware learning. Our journey started with building some simple model. That is, we try to do this relatively simple task-specific inductive bias. That is, we're trying to use the domain knowledge, physics knowledge, and incorporate them inside a graph Laplacian regularizer within the neural network so that we'll be able to improve the predictions. And this is the work that we published in iClear, this RL-GM workshop paper, where we are able to improve the prediction performance using the graph Laplacian regularizer by incorporating the domain knowledge. After this, we quickly realized that adding the domain knowledge as a regularizer is not enough, in the sense that they have a very narrow range where this model can actually work. Because when you have a lot of data, this may not necessarily will give you some significant advantage when you try to incorporate the Laplacian prior. And when we have limited amount of knowledge, a lot of all these PD equations of physical properties also needs data to train on so that they can get the right correct coefficients to generate the effective prior so that it can guide the machine learning model. So that means that basically that we're counting to this particular stage where the narrow range where the domain knowledge can help for the data-driven approaches. And that is when we want to explore a deeper interpretation between observation data, all these physics knowledge together. And that is essentially where we go to this graph neural network. Hopefully that we build a more effective bridge for these two types of information to talk together. And that is basically we build this general inductive biases model, incorporating the domain knowledge to this generalized model that was published in iClear 2020. And later that recently that we built a more specific model where we try to represent this generative bias so that we can help specific tasks using this meta learning, which was published in iClear 2021, which will be presented actually in a few days. And then afterwards that we also want to think a little bit about task-specific inductive bias, where we introduce the concept of domain knowledge and the interplay between domain knowledge and also the causality, because causal inference and causality is also one of the key knowledge we want to incorporate. And we can think of the physics knowledge as one of the causal relationships that we can integrate within the model. And therefore, how we can actually effectively have the interplay between causal information and the physics knowledge, and together with the data-driven approaches. And that is basically we develop also a graph-based neural network, which can effectively handle the causal information together with the physics knowledge. We submit a preliminary results to NeurIPS. And I'm also going to give a little bit highlight of what the model looks like in this talk. So next, I'm going to zoom in more specifically in this generalized model that we published in iClear 2020 to give you a flavor of how we can use this differential graph recurrent neural network to build a bridge between data and also the physics knowledge. So the way that we do this is that we notice that many of the physics-related dynamic equations actually share in the following form. That is, we have the spatial differences, and this can actually be incorporated into this temporal differences. In this way, we will be able to actually use the temporal differences as a function of the spatial differences, and then using them to make a better prediction for the next time step. And that is basically the forecasting task. When we look at the general framework, there are many types of different domain knowledge or physics principles that actually belong to this category. For example, we can have this heat equations, or we can have this convection diffusion equations, we may have the Navier-Stokes equations, all belong to this particular category. And when we look at specific examples, for example, here when we have this heat equation, where we can see the values and locations with different spatial differences will also have an impact on the differences with respect to the time. And if we can incorporate the specific spatial differences and inside the temporal difference, then we will be able to help our prediction. That is a forecasting task. And that is basically where we are as a general idea. We basically build a bridge between the sparse irregular observation time using the relational information represented by the graph neural network. And then we also use the spatial differences and incorporate them inside the temporal differences so that we can build this particular differential signal between the difference between the time, so that we will be able to build a better prediction model using the graph recurrent neural network. The specific architecture of our predictive model, which is we call this as physics-aware difference graph neural network, also we short name as PA-DGN. Basically, the structure is shown as follows. That is, we first are going to have the graph signals at time t, and then we will be able to have the input observations. Based on the input observations, we can construct the graph signals using the graph recurrent neural network. And this is very standard in the machine learning community. And also based on the spatial differential layers, then we're going to build modulated spatial differences, so that we will be able to do a concatenation between the graph signals and also the spatial differences to generate the so-called difference graph. And there are many different types of difference graph that we can generate, which is shown in here. And then in this particular slide, I'm going to show you some specific examples. In this physics-related equations, they typically consist of differential operators. It's very important to approximate the derivatives. In the regular grid, obviously, it's very easy for us to calculate the finite difference approximations at the grid points. For example, here we have our x, and then we will have x minus h, x2 minus h, and or x plus h, x2 minus plus 2h. Then we will be able to get the f prime x using the differences between these different locations, so that we can generate the differential layer. But however, for the irregular grid, the difference operators can be a little bit different. The way that we define it, we can do this either over the gradients of the graph. For example, now we define the delta Fij is the differences between Fj or Fi, and that is the gradients between the two nodes. And then, or we can do this as the Laplacian over the graphs. That means that if we're interested in this particular node Fi, and then the delta Fi will be actually a sum of all the differences from other nodes to this particular node. After we define all these different difference operators, and then this can be the gradient or the Laplacian over the graphs. Now that we'll be able to get the so-called difference graphs. And using the different graphs, then we were going to generate the so-called graphs as a history at time t minus 1 and t minus 2. And then afterwards, we're going to build a so-called recurrent neural network, which will be able to generate the new graph signals at the time t plus 1. So that we'll be able to use the predicted graph signals to make the forecasting in order to get a more robust results. So as you can see, now we will be able to build a channel using the graph signals from the observational data and also from the graph, from the physics knowledge. through the spatial differences. There's some details that I didn't get a chance to talk about. For example, how we learn the parameters associated with the graph differences. Basically, the way we do it is using the observational data to learn local observational data to learn the coefficients. So if you're interested, then you can check out our iClear 2020 paper. They have more of the details in there. Next, I want to show you quickly the experiment results. We have quite a few results. For the interest of the time, I'm going to show you this results that we use the NOI data set from the meteorology observations in 2015. And we're interested in predicting multi-steps. Then we can predict the first time step or predicting 6 or 12 steps. We compare with a few models. Here we have some simple vector autoregressive model. We can use the multilayer perceptron. These are the models that didn't actually consider the temporal, the spatial relationships. And now we also consider, for example, recurrent neural network, graph recurrent neural network, or the RGN. This basically incorporating both the graph neural network together with the physics knowledge was one of the good state of our baselines. And then also our PA-DGN, which is represented with the purple line. Obviously, a general observation we can make is that the spatial information and spatial relation give us a significant boost. The other observations that we can see is that utilizing the graph, the relational information from the spatial differences, we are able to get better prediction performance using the graph, using the spatial information. And also when we incorporate the domain knowledge, for example, when we have RGN or our model, we're able to get even better results. And more specifically, our model will be able to get state-of-the-art results, achieving better prediction performance across pretty much all the different timestamp predictions. And as we have higher, longer term prediction, for example, when we go to the 12 timestamps, the improvement will be more significant. So this is kind of a highlight in terms of how we can utilize the graph recurrent neural network, especially the differential graph neural network, to incorporate the domain knowledge. So next, I'm going to use some time to talk a little bit about the interplay between causality and also the physical principles. So we all know that the physical principles is one type of causal relationship. It is also very fundamental. One of the basic causal relationship in all this physical world is that typically an effect will not occur before the cause, or in other words, the cause will have to appear the effect. And in terms of the temporal aspect, this pretty much means that we will be able to introduce some temporal causal relationships within the physical world applications. On the other side, when we talk about the physical world, that most of these causal relationships are actually not modeled explicitly. So when we think about this, we can do two ways. One is that we can actually learn these causal relationships totally from the data, and that will be actually have a lot of these noise issues, and also the inferred causal relationship may not be as accurate as what we want. On the other side, when we think about this physics knowledge, we can think of them as one of the most direct causal relationships. And these partial differential equations will be able to possibly give us some hint in terms of where the edges could possibly come from. And therefore, maybe there's a way we will be able to fully utilize the partial differential equations so that to help us infer the causal graph and fundamentally to help us in terms of the prediction. Here we gave a simple example where, for example, here we have different type of causal relationships. One of the type could be temporal causal relationship. The other is the spatial causal relationship. And then in here, once we have the diffusion equations in the continuous domain, then this temporal differentiators that we can build using the partial differential equation will be able to give us important hints in terms of the causal relationship. And in this way, hopefully we will be able to build a better model that can actually infer the causal relationship, at the same time make a better prediction model. So that is basically the basic ideas. Here we present one example of how this type of model can look like. So basically now we have our input observations. This can from T until all the history passed to up to K+1. This we will be able to utilize the observational data to generate two types of spatial temporal graphs. One is, we call them STGC, that is a spatial temporal graph on causal inference, where we will be able to try to infer the causal models. And in here, as I motivated earlier, the guiding PDE equations will be able to give us some diffusion equations of continue, for example, the continue or the continuous equations. Then incorporating them together, hopefully we will be able to get and infer a better causal relationship. The second type of spatial temporal graph neural network, we call them as STGV, that is value. That is, we're trying to build a value prediction model. Here we incorporate both the spatial encoder and also the temporal encoder, so that we can build a better prediction building block. And this will be inferred not only through the observation data, but also will be highly guided by the inferred causal graph, so that at the end, we'll be able to get a better prediction performance. So due to the interest of the time, I'm just going to highlight, and now I'm going to zoom into the prediction results. Here that we're looking at the prediction tasks or forecasting tasks for maximum temperature value, minimum temperature value, or snow and precipitation for East Coast and West Coast. Across the board, we can see that our prediction performance will be better compared with other performance. And also, we also see that some of the causal inference model that we're able to get in terms of how for example, the precipitation or the temperature is affected from one location to another location, intuition-wise, it much more agrees with what we have known from the climate experts, because it's more or less guided through the physical principles when we try to infer the causal graph. So I know that I'm running short of time. To just summarize, here we go through our whole journey trying to use the differential equations together with the graph neural network to build a bridge between the sensor information and also the physical knowledge. We got some encouraging results. We hope this opened the door for more exciting and interesting research in this area. So with this, I want to thank the PhD students working on this topic, Song Yang, Trajan, and Sarisa, and also the sponsors for sponsoring our research. So with that, I'll just open up for questions, and thank you very much.
Thank you, Dr. Liu. So it's very interesting talk. Definitely I'll go back and check those papers. I think because of the time, we just do one question on Slido, which is so beyond spatial differences, if there are any other ways that we could use to incorporate edges in the graph. So basically, I think it means like, is there any other ways that one could make connections between these graph edges and physics?
Yeah, I think there are multiple ways that we can do this. So in this particular talk, I give a little bit hint through this causal graph, right, where we can basically using the physics knowledge to guide the causal graph, which will be able to help the prediction performance as well. I personally believe there are also other ways to achieve similar goal. We investigate a little bit. For example, we look at the Koopman graphs theories and trying to look at if there's any other ways that we can incorporate them. I just felt like this graph neural network architecture gave us a lot of opportunities for us to incorporate the information, and hopefully this can attract more people to work on the area. Yeah.
Yeah, thank you.